Before we go on, let's have a small recap. We are trying to model the vibrations of the wings of an airplane with a mass spring system. We have set up a system of differential equations that describes the behavior of this model. In the grasp exercises, we leveraged that the wings have the same masses and we found the eigenvalues and eigenvectors corresponding to this problem. We also found that the general solution of this system can be written in a form that uses eigenvalues and eigenvectors of A. These are the eigenvalues and these are the eigenvectors. The eigenvalues of A are the negative squares of the eigenfrequencies. If the wings start vibrating at a frequency close to one of these eigenfrequencies, there's a significant risk of resonance. But what does that actually mean? Well, to understand this, let's first have a better look at the general solution that we found in the grasp exercises. The earlier exercise on finding eigenvectors wasn't just an abstract math problem, it was directly related to this situation. Eigenvectors describe the characteristic modes of oscillation, while eigenfrequencies tell us how fast these oscillations occur. Here is the general solution when we focus only on the terms involving cosines. The values omega1, omega2 and so on are the eigenfrequencies of the system. The constants C1, C2, C3 depend on the initial conditions of the system, such as the initial displacement and velocity. What's especially interesting is the role of the eigenvectors. Each eigenvector corresponds to a specific mode of oscillation, defining the direction and relative motion of the system's components. These eigenvectors shape the oscillations by determining how the motion of one part of the system relates to the other. When multiplied by the cosine functions, the eigenvectors create a unique, well-defined pattern of vibration. We found that one of the eigenvalues was 0 and the corresponding eigenvector 1, 1, 1. This does not correspond to an oscillation because the cosine of 0 is 1. It's just a plane moving like a rigid body. Since this is a case that we are not interested in, we will use only 2 eigenvectors and 2 eigenvalues in the final solution. To show you how these oscillations look, we would need to substitute some numbers to be able to plot it. Let's assume that m2 is 3 times n1, so the wing is 3 times lighter than the fuselage. Let's first examine the first mode of oscillation. In this case, the corresponding eigenvector is -1, 0, 1. This means that the second mass, the fuselage, remains stationary, while the 2 wings oscillate in opposite directions. This is the characteristic shape of this oscillation. What about the second term in the general solution? The eigenvector for this mode is 1 minus 2 over 3, 1. This indicates that when the wings move in one direction, the body of the plane moves in the opposite direction. The resulting motion looks like this. Finally, we will discuss resonance. What happens if an external force acts on the system with a frequency that matches one of its eigenfrequencies? You may recall from your calculus course that when this happens, a factor t times cosine appears in the solution. In this case, the response is no longer just an oscillation, it leads to an unbounded increase in amplitude over time. And this is what we call resonance. It's like pushing someone on a swing at just the right moment. Each push adds more energy, and the motion becomes increasingly amplified. In the case of the wings, this can lead to dangerously large oscillations and even structural failure. If this concept feels unfamiliar, it is worth revisiting your calculus textbook to review solutions of differential equations with resonance behavior. To conclude, the parameters k, m1 and m2 must be carefully designed so that the resulting eigenfrequency can never coincide with common turbulence frequencies. This is crucial for ensuring the structural safety of the aircraft. By solving the eigenvalue problem, you don't just prevent your airplane from resonating dangerously during turbulence, you also gain insight into the specific shapes and frequencies of its natural oscillations. Thanks for watching and see you in class.